All right. So I'll still give you a quick run through of where we were last time, and we kicked off recursion. Right. So quickly, and now since you've done that, probably that could be a quick brush up for you, right? The session needs to be interactive, and I'll make sure that you answer. You guys talk about it. Recursion. Recursion means something which is repeating in a pattern, right? Now, how in the purview of the book, we've got two kinds of patterns that we're going to study. The first pattern that we've kicked off here last week was arithmetic sequence, AS. And the other side is the geometric sequence, which is still to learn. Now, arithmetic sequence and geometric sequence, the prime difference between the two is that arithmetic sequence, you get something either added or subtracted. Added or subtracted, right? And in geometric sequence, we got something either multiplied or basically divided. Right. Again, division is one form of multiplication as well, right? If I divide a number by let's say the number is 30, divide by 3, I can also say I'm actually multiplying it by 1 over 3. Right? So basically, how you see the world. Right? Now, coming to arithmetic sequence, this number which is either getting added or subtracted is called common difference D, and we'll talk about here later. So for example, if I say I've got a sequence like 2, 5, then 8, and say what is the next number? So you'll say, okay, it's 11 because you're going up by 3 every time, right? So the next number will be 11. What is the common difference here? 3. When you graph this sequence in such a way, the term number is here and the term value is here, so V. This is the term number N. This is T0, term number 0. I can also call it as V0, T0, A0, B0, depending upon different books, right? Cambridge calls it as V. Right? V or T is interchangeably used in Cambridge. So this is V1 and V2 and V3. So if I say, okay, this is V0, V1, V2, V3, V4, and these are the values of the term. So 2, 4, 6, 8, etc. So what you will see is a graph like this, a straight line graph, a linear graph. So for arithmetic sequences, the graph is linear, straight line. Now, if your D is a positive number, the graph has a positive slope. And what do you mean by slope? Rise over run. That means as x increases, y increases. You'll have a line like this. And if your D is negative, let's say negative 3, so your sequence could be 11 in the reverse order. 11, 8, 5, 2, and so on. So you are jumping by -3 basically. So in that case, your sequence or your graph will be like this. That is how your points are going to be. Alright? So here the slope is negative. So far so good with me? No one's lost yet? Alright. Now, on arithmetic sequences, I don't have to write my sequences every time, as in there's no end to it. Where do I stop? So there is a way that we represent our sequences, not by just writing the term numbers, but by a rule. We call it as, or a relation, we call it as recurrence relation. Sorry about my spellings. But then this is not an English class, right? So recurrence relation means has two parts to it. The first term and a rule to generate the next. So for example, if I pick up the sequence, I've done that all of that right last week, but I'm just giving you just because we're going to move forward. The first term is always given to you. So this tells you where to start. And then you are given a rule, and it's a Vn plus 1 equals to V0, so Vn plus 3. That's the rule. So that tells you that in order to go to the next term, so if you want to go to an n plus 1, what you need to do is you need to add 3 to Vn. Right? So 3 here is the D, the common difference. So now if I write something like this, I say V0 equals to 5 and Vn plus 1 equals to Vn minus 4. Can you generate the first 4 terms? What will be the first term here, Gary?
5.
What will be the next term here, Michelle? Danu, what's the next term? Negative
3.
2.
Oh, 2.
2. Negative 2. 1 minus 4. What is the answer?
Negative 3.
This is negative 3, right? We're talking about negative 3? Yes. Yeah. So negative 3 and you keep going. So this helps you to generate recurrence relation. The term itself. So this is the recurrence relation, right? Now, coming back to, shall I take this off the board now? Tanu, can you give me an example, a practical example of arithmetic sequences? Any real life example of arithmetic sequence, please? Any real life example? Of arithmetic sequence is simple interest. We talked about in depth simple interest and compound interest, right? Simple interest, and the real life example of geometric sequence could be compound interest. What is the difference, Michelle, between simple and compound? You did that.
You can. I actually forgot the difference.
Yavi?
In compound interest, it's like the value changes, and then that's what the interest is becoming. Whereas simple interest, no matter what you start off with, if the interest keeps increasing, the value of the original number does not increase. Whereas in compound it does.
Danu, what's your take on it?
In simple, so like what you like add or minus stays the same. But like in compound, it's like the original one that you have to like. I'm not sure how to like explain it.
Kinda. I'll give you an example. Let me know, and Joe, you as well. Let me know which is this interest. I invested $1,000, and the bank is paying me 10% per annum, which means every year. So 10% is what? $100. let's say the bank keeps paying me $100 every year. Which interest? It doesn't change. See, at the end of first year, if the bank's giving me $100, my balance would have been $1,100, right? So ideally, I should have got 10% of $1,100 rather than 10 of the original amount. But bank doesn't care about it. Just keep paying me $100. So my balance just keep going in the multiples of 100, even if the balance far more than $1,000, right? So I lose some interest here. That is, so my common difference between them is always 100. You see, that's a sequence, right? 1,000, 1,100, 1,200, 1,300, and you go on. So a common difference is 100 always. This is a classic example of arithmetic sequence. Does that make sense? Whereas in compound interest, Michelle, you started with 1,000, same interest rate. First year you get 100, so your balance became 1,100. Now next year you will get 10% of the last amount, so you get $110. So your balance would be 1,100 plus 110, so 0,121. So you get $10 more than someone who's sitting on simple interest. Make sense? Yes? This, and you keep going. So next year you get what? $121, 10% of 1210. This is the world of geometric sequence, geometric growth sequence. So sequences are of two types. When your common difference is positive, we call those sequences as growth sequences. When something grows, money grows, bacteria grows, population grows. When something grows, it's growth. But when something is growing on a constant basis with the same amount, with the same unit difference of time, we call it as arithmetic growth. And then if your D is a negative number, in real life world, if your amount, if the amount is going, if something's going down by the same amount let's say every year, I call it as decay or dep or depreciation. Have you heard of that word depreciation? What does depreciation mean? Michelle? Going down. And what can go down with time, Danu? What values go down by time with time generally in our lives? Okay, that opens up another subject altogether. Give me an example of liability.
Let's say your iPhone.
Exactly, your phone. You bought it for, let's say $2,000, but then you use it for a year, it's like worth $1,000. So value's gone down. That is depreciation or decay. Now, if the value goes down every year by the same amount, so let's say, Danu, you've purchased an iPhone for $2,000, and let's say you're using that iPhone for X number of years, and you've been told that your value of your iPhone goes down by $200 every year. So after 4 years, how much would be the value, Gabby? After 4 years,
1,200.
1,200. 4 years times 200. Negative 200 is negative 800. So minus 800, you become $1,200. This is called depreciation, and I'll use another word. It is called flat depreciation. Yes, Danu? Makes sense? Flat depreciation means same amount going down every year. Have you heard of something called unit depreciation? Anyone? Danu, have you heard about it?
No.
Any idea? Can you explain? Probably. That's fine if you can't.
No, I'm not sure.
No? Alright. Unit depreciation. Now, unit depreciation. Shall I take this off? There's too much noise on the board. Is that okay? Shall I? I'm covering a lot of concepts straight off rather than going chapter by chapter, right? I'm covering a lot of chapters and then we'll jump on and we'll do the question. We'll do a mixed bag of questions, okay? Because they're all interconnected. Now let's talk about, so we've talked about the dep or the depreciation. We talked about growth and you've got the decay. And your decay has a depreciation and your depreciation has two types, flat and unit. We just understood what flat is. Same amount going down irrespective of your usage. Now if Danu, you're using your phone 23 hours a day for next 4 years and I say no, that's fine, it's still dropping by $200 every year. And even if it's broken, you got it fixed, it got scratches, etc., I don't care, 200. That is flat, right? But then let's say I'm just trying to make a problem now, which is more iPhone and connects the dots here. So let's say I've installed an app on your phone, the screen timer app, right? And I say, okay, every 10 hours of usage, 10 hours of usage of your phone drops the value by 50 cents. 50 is harsh. Let's say 10 cents. Every 10 hours of usage. Now I'm not worrying about how many years. I'm not worrying about the usage, the unit. How much you are using. So now, let's say, Danu, you've used your phone for 2,000 hours. Can you tell me how much money it will go down by?
20.
Sorry?
$20.
So you will say 2,000 divided by 10 times 0.1, which is $20. Yes, Gary, makes sense? Now you suppose this $2,000 were used for a period of 1 year. 1 year. So this is what you've lost in a year. So if you go and sell that phone after a year, you would have got like what? $1,980, right? Whereas in the world of flat depreciation, it was going down by $200 flat, so you would have got what? $1,800. You saw the difference? This is called the unit depreciation. Classic example is printer. So your depreciation on printer in commercial world is how many prints you are making, not for how many years you've held that printer. Car is a classic example of unit depreciation. You know, if you've kept that car for a year, but then you've clocked 100,000 kilometers in a year, obviously your value will go a lot down, right? So the car is a classic example of unit debt. Printers are a classic example of unit debt, and so on and so forth. I just made one for you right here. Right? Make sense? All good? Yeah. Any dramas so far? No? Michelle? Are you okay? All right. Let's go to page number 357 of your book, and